Hello, everybody. Hey, this is a lecture on measurement and significant digits. Now, in science, we are constantly making observations in order to test hypotheses, in order to come up with some conclusions. Now, in those observations, there are two types. There are qualitative, like warm, fuzzy, things like that. And there are quantitative observations, which would be something like 92 degrees Celsius, or something along those. So these are qualitative observations. Qualitative observations are measurements, and measurements are going to have at least two components. Okay, they're going to have a number and a unit. They're going to have a number and they're going to have a unit. Okay, so when we have, for example, I have a height of 6 feet. Now that 6 feet is about 1.83. Okay, so 1.83, and then the unit would be meters. Okay, so that has a number and a unit. And if I were to say 6 feet, okay, if I were to say 6, okay, then that would be a different unit. Okay, so in both cases there is an observation about my height. Okay, and one would have a number and a unit, another one have a number and a unit. So we can see that without having the unit, the number essentially becomes meaningless because we're measuring the same thing. And one, we get a number of 6, and the other one, we get a number of 1.83. So we definitely need both of those. Now, as we've also talked about with vectors, we could also have a direction that is on top of those measurements. But that will not change what we have when we're talking about significant digits. Now, here we can see that this right here is a meter stick, okay? And I am going to arbitrarily measure the distance. I'm going to arbitrarily measure the distance between one point and the other, okay? So if we look here and we know that this is a meter, okay, the whole length is a meter, but obviously this is less than 1 meter. And whenever we are measuring between 2 points, so this would be 0 and this would be 1 meter, okay, we can estimate what that is. So if we do this, okay, I'm going to estimate that that is about 0.5, okay? So my first observation is that it is equal to 0.5 meters, okay? We can estimate the difference between this. Now this right here is a guess, okay, or an estimation. Now, all qualitative observations, number, unit, is going to have a guess. It is going to have a guess. Now, obviously, this right here is simply still a guess, all right? So now let's get a little more precise. So now if we look at this meter stick, now it has divisions between the red, or between the white and red and white and red. All those are a decimeter, or 10 centimeters, or a tenth of a meter. Okay, so now we're going to make the same. We're going to make the same measurement. Okay, but now we're going to use this side, and now we can see right here that we've got 1, 2, 3, 4, 5. Okay. And now we've got this little section here. So in this little section right there, we can guess, because now we're between two divisions. And I'm going to guess that that is a 2. Okay. And this right here, okay, and I'm going to do this a little bit different here. I'm going to say 0.52. Okay. So this last number right there was our guess. But on this one, this was certain. Okay, it was certain because when I measured it, it was at least 1, it was at least 2, 3, 4, 5. So since it went past the number of that 5 decimeters, I know for certain that it's at least 5. And after that, it doesn't quite get to 6, so we're going to estimate in between. So now, this case, this measurement has one certain figure and one guess, or one estimation. So now we're going to now use a meter stick that has smaller divisions. And the first smaller division that I'm going to use are centimeters here. So these are numbered, okay? And now I'm going to number that, and now I can see that it is 51.5. Okay, so now I'm going to say 0.515 meters. 0.515. So when I got down to here, this was my guess. It was somewhere between 51 and 52. It was somewhere between 51 and 52. So I estimated that it was halfway. Okay, but the 51 centimeters I was certain about because I read it off of my instrument. I read it off of my instrument, so I know for certain that it went past that. Now I'm going to do that again. Okay, but now I'm going to use the smallest divisions here, and I am now going to say that that is 51.5. So 0.517 okay, let me read 0.5175 meters. Okay, so this is 517.5 millimeters. This is 51.5 centimeters. This is 5.2 decimeters. This is a half a meter. Okay, and that is kind of the beauty of the metric systems. We can call it all different components there, but they are all essentially going to be in the same family of meters, and we're just going to use prefixes in order to distinguish them. Now, I want to point out that in every one of these measurements, even the first one, we had a guess. And in these other ones, we also had these certain figures. Because we are good at estimating between marks, okay, even though it's a guess or uncertain, okay, they all count, okay? So we're going to say okay, significant figures are all of the certain plus 1 guess. Okay, now that guess is uncertain. So all of the certain plus one uncertain. Okay, so how uncertain are you? Okay, now with any instrument that has been calibrated, for every instrument that has been calibrated, there is going to be a understood precision. And what I mean by precision is plus or minus one of the last placeholder that our last significant digit or our uncertain figure is. So when we look at this one right here, okay, this is going to be plus or minus 0.1 meters, plus or minus 0.1 meters, because our last or uncertain thing was in the tenth of a meters, so we get a precision of plus or minus a tenth of whatever that placeholder is. The placeholder was in the tenths place, hence plus or minus 1/10. Okay, now when we go to the next one, that's going to be plus or minus 0.01 meters, plus or minus 0.001 meters, and plus or minus 0.000 meters. Okay, so what does that mean? That means the correct answer, the accurate answer, okay, is going to be somewhere between 0.4 and 0.6, between 0.4 and 0.6. And the next one is going to be somewhere between 0.51 and 0.53. And the next one is going to be somewhere between 0.514 and 0.516. And the next one is going to be somewhere between 0.5174 and 0.5176. So we can see here that in each case, our guess is getting narrower and narrower and narrower. We are becoming more and more precise, more and more precise. Now, I just said that if your instrument is calibrated, okay, now in order for an instrument to get calibrated, the manufacturer is going to make lots and lots of different measurements, and they're going to see how close they are to each other. Okay, so precision is a measure of how close a number of how close a number of measurements are to each other. Okay, and if they all become within essentially a tenth of the last division, then the manufacturer is going to be sure that it is going to have an instrument that falls within the assumed precision, So when we go to a meter stick that has millimeter marks, that means we know that we can rely on this device to be plus or minus a tenth of a millimeter, okay? Where if we were using this one, if this is all we had, okay, this being a meter, well, we only have 2 marks, so this is going to be plus or minus a tenth of a meter. So if we went around trying to calibrate this, we would measure, have a bunch of people measure the same thing, and we might get 0.5 and 0.6 and 0.4 and 0.5 and 0.4 and 0.5 and 0.5 and 0.6. And we statistically take all those and we realize that all our measurements end up being at 0.5 plus or minus a tenth of that, then we can certify that this would be calibrated to plus or minus a tenth of a meter. Okay, and if we use this and we calibrate this, then our precision just went up by 10. Okay, now, if we said this right here, if we went and used this, for example, and we said that this was 1.5, okay, if we said the length from here to here was 1.5, okay, then clearly we're wrong, okay? So accuracy is not the same thing as precision. Accuracy is not the same thing as precision, although they are related, okay? Accuracy is how close a measurement is to the correct or the accepted value, okay? So sometimes we don't know, but essentially we don't know what the correct answer is. And so what happens is that we will do multiple measurements, and then as a community, as a scientific community, people are going to say, hey, the correct answer is this, and you're going to measure your measurement for accuracy compared to the accepted value, okay, or if we know, okay? So that's precision and accuracy. So every measurement can be accurate, and there's always going to be a precision. Is that accuracy plus or minus 0.1, plus or minus 0.01, 0.001, 0.0001? So there's always going to be a degree of precision in every measurement, even though you might be wrong. Okay, so this might be what you remember when you talk about learning precision, let's say in a chemistry class. Okay, so if we had a bunch of darts and we're going to end up here with 4 targets, okay, we'll just assume that they're the same, and we're going to throw 3 darts. And if we throw a dart that comes in, let's say right here, and a dart that comes in here, and a dart that comes in here, okay? Now, is that accurate? And how precise is that? Now, again, we end up having this spot right there, and this spot right there, and this spot right there. So now we can see that those darts, if we were aiming for the middle, are pretty spread out. But if we were to average those, their average would come out to be in the bullseye. So even though those measurements are not very precise, they're still accurate. They're still accurate, okay? Now, if we had another set and we had, let's say, this dart that hit here and this dart that hit here, and then we had another dart that hit here, okay? Now we can see that all of those darts are really close to each other, and we're aiming for the bullseye, okay? So since we did not hit the bullseye, we would be inaccurate, okay? But because all our measurements, all our darts were really close to each other, then they would be more precise, okay? So we could have something, a dart that's way out here, and another dart that's here, and another dart that is, let's say, here, okay? Now, those are really spread out, so they're not precise. And if we average them out, okay, if we somehow took the average, then they're not going to be very precise. So this is neither accurate nor very precise. Now remember, I said very precise. There's always a precision. There's always going to be a precision. But if it's a big precision, that's not as precise. If you have a very small precision, then you could be right or wrong. So what we're really aiming for here in any series of measurements is going to be, if, for example, we were aiming for the middle, we had 3 darts, they're really close together. That means they're more precise, but they're also within the target. That means they would be accurate. All right, so that's kind of the basis. That's kind of the basis for the idea behind significant figures, okay? Now, there is going to be a whole set of rules for significant digits, and rules for when you add and subtract, and rules for when you multiply and divide, okay? So I'm going to get rid of this, okay? And, okay, so rule, okay, rule number 1, all non-zeros are significant. So all non-zeros are significant. That's 1 through 9. 1 through 9. Now remember, significant could be a guess or it could be certain, depending on the measurements. 2, leading zeros are never significant. So here's an example. 0.002. Okay, these are leading because they come from the left. So when you want to know if they're leading zeros, you go from left to right, and any zeros that come before a non-zero, like 2, they are leading zeros and they're never significant. Okay? Captured zeros are always significant. And an example of a captured zero would be 303. 303. So this right here is captured. So any zeros between non-zeros, are going to always be significant. Okay, which leads to our last rule, which is going to be trailing zeros. So trailing zeros are sometimes significant. There's times when they are, and there's times when they're not, which I will talk about. But a trailing zero is going, for example, going to be 3000. Okay, that's a trailing zero. Or 3.1000. Okay, those are trailing, and these are trailing. Okay, they're going to come after the last non-zero number. So moving from left to right, you count the zeros after the last non-zero, and those would be trailing. Okay, so two parts here. If no decimal point, they are not significant. Okay, so those 3 zeros are not significant. Then if they're not significant, then why are they there? Okay, these become placeholders. Okay. So for example, if you had 3 kilometers, if you measured something that was 3 kilometers, okay, but you wanted to change that into meters. Now, if again, you're guessing about 3 kilometers, so that's going to be somewhere between 2 and 4 kilometers. But now you wanted to change kilometers into meters, you'd multiply by 1,000. So then you would go 3,000 meters. But your measurement's still the same, so you should still only have 1 significant digit. So the only reason you put in those zeros were as placeholders. Okay, still has 1 significant digit. Okay, so part B, if there is a decimal point, then they are significant. So if you have a decimal point in the measurement, now it only counts for trailing, okay, but then they're going to be significant. Okay, so these 3 zeros, those 3 zeros in that measurement are significant because they're trailing with a decimal point. These 3 zeros have no decimal points, so they're not significant. So how would you get a 0? How would you get a 0 as a guess? Okay, so that's really what that guess is. So this 3.100, those would all be certain. And this last zero would be your guess. Well, if you are measuring something and you think it is exactly on that position, okay, exactly on the line, then your guess for the uncertain figure would be 0 because you're exactly on the line. And that's how a 0 on the end can be significant. Okay. All right. A couple more rules here. And one is when you're adding and subtracting. When you're adding and subtracting, your answer to a sum or difference can be no more significant than the least significant number in your calculation. Okay, so what the heck does that mean? So if we had 3.01 plus 0.235, let's say we were in centimeters, okay, and we were to add this together, we would get 3.245, okay, centimeters. And we would have to round. We would have to round this number, okay? Now remember, if we look at this one, this number right here is plus or minus 0.01. We go to the last placeholder of the last significant digit, the guess, and we're going to go plus or minus 1, whatever that is. Now, when we do it here, for this one, it's going to be plus or minus 0.001. Now, remember, even though that's a 5, we go to the plus or minus 1 of the placeholder. Okay, so that's going to be plus or minus 1. So when we look at these two numbers, okay, we can see that this 3.01 centimeters is less precise than this one right here. In fact, it's 10 times less precise. So we need to round it to plus or minus 0.01. Now, one way to think about this is if we line up our decimal points, and then we can just kind of go from right to left here, and we can see However far this arrow goes to the left, whichever one goes farthest to the left, that's going to be the least precise. So now we could take this line down here, and we could say, does the 5 round up or down? Okay, and if we say that it rounds up, then our answer would be 3.25 centimeters. Okay, and that would be the answer. So that's the rules for adding and subtracting significant digits. It's always about not wanting any uncertainties to come into our calculations, okay? All right, now we're going to have multiplication and division. The answer to a or okay, so when we're multiplying and dividing, our answer can have no more number of significant figures than the fewest in our calculation, okay? So this is going to come up to counting significant digits, which goes back to these rules right here. So let's take our 3, what do we have here? 3.01 times 0.235. 3.01 times we have 235.235. Okay. Now 0.235. So now if we do the math there, okay, then we're going to say 3.01 times 0.235, and our answer is going to be 0.70735. Okay, 0.70735. So let's say again this was centimeters and centimeters, but when we multiplied, that would give us centimeters squared. So if you're thinking that this looks way too precise, you are correct. You need to round it at some spot. Okay, but now we're no longer seeing how precise this measurement is. We're seeing how many significant digits there are. So if we go to the top one here, we're going to have 301. Okay, now these non-zeros are always significant. The zeros, that's really the question there. Now remember, this zero is captured. That zero is captured, so it counts. So we have three significant figures here. And if we look at this one, we've got 0.235. Now this zero is leading. This zero is leading. And so it doesn't count. Now we're going to start counting when we get to the first non-zero, which is 235, so that would count as 3. Let's just say that we had 0, 0. We had 0, 0 right there, which meant because these are trailing and there's a decimal point, these would count, and we would have 1, 2, 3, 4, 5. We'd have 5 significant figures. Okay, 1, 2, 3, 4, 5. So if we base it on this, we'd have all of these numbers, but we have to base it on the fewest. So we got to round to 3 numbers. So we're going to go, this 0 doesn't count, so we're going to go 1, 2, 3. And now we're going to say, we're going to look at this 3. This is where we have to round. Does that 3 round up or down? We say it rounds down. And so our answer is going to be 0.707 centimeters squared. Okay, and that is how you round when you multiply and divide. So division is kind of the same thing. Okay, almost done here. If we have a number in scientific notation, let's say 3.2 times 10 to the third, 3.2 times 10 to the third, and we want to know how many significant digits there are. Okay, well, we just have to look at the numbers that are in front of the times 10 to the third. Okay, and right here, there's only 2. So this one in scientific notation only has 2 significant digits because the 3 and the 2 are non-zeros, so they always count as significant. Okay, well, what if we have 51 million? Okay, if we had 51 million centimeters and we wanted to change that into scientific notation, okay, we're going to say 5.1. Now, where do we, so it's really going to be 1, 2, 3, 4, 5, 6, 7. So it's going to be 5.1 times 10 to the 7th centimeters. And we want to just count. We want to just count the numbers that are significant, okay, which these are trailing zeros with no decimal point. Trailing zeros with no decimal point are not precise. So the only 2 we have is here, and that's going to be reflected down there. Okay, well, what if we had a decimal point right there, okay, and we wanted to write this in scientific notation? We would have to say 5.1000000 times 10 to the 7th, and that would be centimeters, because this is a lot more precise than this. Well, what if our precision, ended up right there, okay? So sometimes it's difficult if you have the choice between either 52 million or the decimal point all the way down here. If you're somewhere in between, it's kind of tricky. So the old school way to do it is if it's a 0 and you have a bar of it, that's your last significant part, then you can say 5.10 times 10 to the 7th centimeters. So if you know you are plus or minus 100,000 as opposed to plus or minus 1,000,000, you can put a bar right there, and that's indicating that you're plus or minus 100,000 as opposed to plus or minus 1,000,000 as opposed to plus or minus 1, okay? And then you could make your scientific notation like that. All right, you guys, I think that covers it. And if you have any questions about this, you can ask me, and we will also come up with examples as we move along in our problems. All right, take care.